Okay, let's continue with the question and answer discussion. The rules for linear combination of atomic orbitals are as follows. Conservation of orbitals. The total number of orbitals before and after linear combination must be same. For example, if you combine two atomic orbitals, you should obtain two new molecular orbitals. Conservation of energy. The total energy of the system should be conserved. This means that the energy of the combined molecular orbital should be equal to the energy of the original atomic orbitals. Conservation of symmetry. The linear combination should preserve the symmetry of the system. This means that if the original atomic orbitals have a particular symmetry, the combined molecular orbital should also exhibit the same symmetry. Orthogonality. The molecular orbital obtained from the linear combination should be the orthogonal to each other. This implies that the wave functions of the molecular orbital should be perpendicular to each other. Coefficients. The linear combination involves multiplying the atomic orbital by appropriate coefficients. These coefficients determine the contribution of each atomic orbital to the resulting molecular orbital. The coefficients can be positive or negative or even zero. Normalization. The resulting molecular orbital should be normalized, meaning that their integral squares should add up to 1. This ensures that the probability of finding an electron in the molecular orbital is 1. These rules guide the process of combining atomic orbitals to form molecular orbital in the linear combination of atomic orbital method, which is commonly used in molecular orbital theory to describe the electronic structure of the molecules. With this, we'll go to the next slide. Okay, this we discussed already. And catalytic poisoning. Catalytic poisoning is a process in which a catalyst is rendered inactive by the presence of foreign substances. The foreign substances, called a poison, can bind to the catalyst surface and prevent the catalyst from reacting with the reactants. Catalytic poisoning can occur in variety of industrial process, including the production or manufacture of ammonia or sulfur and also plastics. It can also occur in some household products such as catalytic converters in cars. Here are some examples of the catalytic poisoning. In the production of ammonia, the catalyst is iron. If the iron catalyst is exposed to a oxygen, the oxygen can bind to the iron surface and prevent the iron from reacting with the nitrogen and hydrogen gases. This can lead to a decrease in the yield of ammonia. In the production of sulfuric acid, the catalyst is vanadium pentoxide. If the vanadium pentoxide catalyst is exposed to sulfur, the sulfur can bind to the vanadium pentoxide surface and prevent the vanadium pentoxide from reacting with sulfur dioxide and oxygen gases. This can lead to decrease in the yield of sulfuric acid. In the catalytic converters, the catalyst is a mixture of metals such as platinum, palladium, and rhodium. If the catalytic converters is exposed to lead, usually you can observe that lead-free petroleum products. If the lead is contained in petroleum product, that can deactivate the catalytic converters. and the lead can bind to the catalyst surface and prevent the catalyst from reacting with carbon monoxide, nitrogen oxides. Carbon monoxide, nitrogen oxide, and hydrocarbons, these are the byproducts of the fuels or automobiles, and these will enter into the atmosphere. This can lead to increase in emissions of harmful gases from cars. Let's go to the next slide. Explain molecular interpretation of entropy. What is the Michaelis-Menten mechanism? Write Arrhenius equation and indicate the terms involved in it. So this molecular interpretation of entropy we discussed previously in previous video. So I will go to the next slide. Michaelis-Menten mechanism is a fundamental concept in enzymology that describe the kinetics of enzyme catalyzed reactions. It provides insight into how enzyme react with the substrates to form product. The mechanism is named Michaelis and Menten, who proposed this in 1930. Michaelis-Menten mechanism consists of following steps. Enzyme substrate complex formation is the first step. Enzyme react with the substrate, bind it together to form an enzyme substrate complex. This is called ES complex. This step is typically reversible and can be represented as E plus S equilibrium with ES. Product formation. Once the enzyme and the substrate are bound in the ES complex, a chemical reaction takes place resulting in the formation of product. This step is irreversible and can be represented as ES gives rise to enzyme. This is called regeneration of the enzyme and product is obtained. Enzyme regeneration. After the product is formed, the enzyme is released and can bind to another substrate molecule. So repeat the catalytic cycle. The rate of reaction can be described by the Michaelis-Menten equation, which relates the reaction rate V to the concentration of the substrate and the other kinetic parameters. That is reaction, enzymatic reaction rate V is equal to Vmax into concentration of the substrate upon Michaelis-Menten constant and substrate concentration. Here, Vmax represents the maximum interaction rate when the enzyme is saturated with the substrate. Km is the Michaelis constant, represents the substrate concentration at which a reaction rate is half of the Vmax. It is a measure of affinity between the enzyme and the substrate. Lower Km values indicates the higher affinity. Let's continue this in the next slide. The Michaelis-Menten mechanism assumes that rate determining step of a reaction is the conversion of ES complex into product. And it assumes that the concentration of enzymes remains constant throughout the reaction. The mechanism provides a useful framework for understanding the enzyme kinetics and predicting the behavior of enzyme catalyzed reactions. It helps elucidate factors such as enzyme substrate binding, the formation, and the breakdown of the ES complex. The influence of the substrate concentration on the reaction rate. This will be the a 2 marks question, Arrhenius one. The temperature dependence of the reaction rate is described by the Arrhenius equation, which relates the rate constant K of the reaction to the temperature T and the activation energy EA. The Arrhenius equation is given by K is equal to A into exponential to the minus EA by EA upon RT. Here, K is the rate constant of a reaction, A is the pre-exponential factor or frequency factor, which represents the rate of molecular collision and the probability of the successful collision. EA is the activation energy, which is the minimum energy required for a reaction to occur. R is the universal gas constant, that is 8.314 joule per mole per Kelvin. T is the absolute temperature. With this, I will go to the next slide. Here, a question: what are extrinsic and intrinsic semiconductors? So this is related to metals. Intrinsic semiconductors are the pure semiconductors, meaning they do not contain any impurities. They have a smaller number of free electrons and holes, which are created by the thermal energy. The conductivity of intrinsic semiconductor is very low at room temperature, but increases with increasing temperature. Extrinsic semiconductors are the semiconductors that have been intentionally doped with the impurities. The impurities can be either donors or acceptors. Donors are atoms that donate electrons to the semiconductor, while acceptors are atoms that remove electrons from the semiconductor. Doping with the donor creates N-type semiconductor, which has an excess of electrons. Doping with the acceptors create a P-type semiconductor, which has an excess of holes. The conductivity of extrinsic semiconductor is much higher than that of the intrinsic semiconductor. With this, let's take one more question. Explain catalytic poisoning, more particularly for 2 marks 1. Catalytic poisoning is the partial or total deactivation of the catalyst by a chemical compound. Catalyst poisoning can occur when poison molecule bonds to the active site of the catalyst. The active site is the location on the catalyst where the reaction takes place. When the poison molecule binds to the active site, it prevents the reactant molecule from binding the reacting. Let's take one more question. Calculate the bond order of a NO molecule. NO means nitric oxide. The bond order of a molecule is the number of shared pair of electrons to atoms. It can be calculated using the following formula. Bond order is equal to number of bonding orbitals minus number of anti-bonding orbitals. Total number of electrons present in nitrogen is 7. Total number of electrons present in oxygen is equal to 8. Totally it is 15. Apply MOT. Here you can understand that these are the anti-bonding. Star 1 is called the anti-bonding. So bond order is equal to number of bonding electrons minus number of anti-bonding. Anti-bonding on 5 is there, bonding or 10 is there, 10 minus 5 by 2, that is equal to 2.5. Is the bond order of a NO molecule. Let's take one more question. Write BET equation and indicate the terms involved. BET equation for the multi-layer adsorption. P upon V P naught minus P, that is equal to V upon VMC plus C minus 1 by VMC and P upon P naught. Or it can also be written in the form V is equal to VMCF upon 1 minus F into 1 upon 1 plus C minus 1 into function F, where V is the volume of the gas reduced to STP, adsorbed at a given pressure P and constant temperature T. Vm is equal to volume of a gas reduced to standard temperature pressure, adsorbed when the surface is completely covered by a unimolecular layer. F is equal to P upon P naught, where P naught is the vapor pressure at the external temperature T. C is equal to a constant at a given temperature, that is E is E1 minus EL upon RT. So here E1 is equal to heat of adsorption of a gas in the first layer. E2 is equal to heat of liquefaction of a gas. So let's take one more question. What is the limiting radius ratio for a coordination number 4? For a coordination number 4, the limiting radius ratio ranges from approximately 0.155 to 0.225. Mention any two limitations of the octant rule. Incomplete octant. Some elements, particularly those in the second period, such as beryllium and boron, tend to have a fewer than 8 electrons in their valence shell. These elements can form a stable compound even though they do not achieve a full octet. For example, beryllium commonly forms compounds like beryllium chloride with only form 4 electrons around the central atom. Expanded octet. As mentioned earlier, elements in the third period and behind, such as phosphorus, sulfur, and chlorine, can accommodate more than 8 electrons in their valence shell due to the presence of empty d orbital. This allows them to form a compounds with the expanded octets, such as phosphorus pentafluoride or sulfur hexafluoride. Odd electron species. Some compounds contain atoms with an odd number of valence electrons, such as nitric oxide, NO, nitrogen dioxide, NO2. These species cannot achieve a full octet due to the odd number of electrons, but they can still be stable and exist. Transition metals. Transition metals often do not follow the octet rule due to their variable oxidation states and involvement of their d orbital in bonding. They can form compounds with incomplete or expanded octets depending on the specific situation. Let's go to the next slide. State isoelectronic principle. The isoelectronic principle states that atoms in a molecules that have the same number of electrons which have similar chemical and physical properties. This is because electrons in these species are arranged in the same way, regardless of the identity of the nucleus. O2 minus, fluoride anion, and magnesium 2 plus. These three species all have 10 electrons and isoelectronic with each other. They have similar chemical properties, such as being able to form ionic compounds with cations. Nitrogen dianion, carbon monoxide, and nitric oxide ion. These three molecules all have 14 electrons and are isoelectronic with each other. They have similar chemical properties, such as being able to form a covalent bond. Let's go to the next slide. What is zero order reaction? Give an example. These are reactions in which rate of reaction independent of the concentration of all the reactant. For example, reaction of hydrogen gas with chlorine forming a 2 hydrogen chloride molecule. Here rate is H20 and Cl20. That means zero order reaction. Decomposition of HI on the gold surface at high temperature. HI undergoes decomposition in presence of gold, gives rise to hydrogen and iodine. In the presence of catalyst, the reactants are absorbed onto the surface of the catalyst, and reaction takes place only on the surface of the catalyst. That is the reason in these two examples of the reaction, rate is not depends on the reactants. Let's go to the next slide. So write a Arrhenius equation, mention the terms involved in it. The temperature dependence of a rate reaction rate is described by the Arrhenius equation, which relates the rate constant K of a reaction to the temperature T and the activation energy EA. The Arrhenius equation is given by K is equal to A into exponential to the power of EA minus EA upon RT. K is the rate constant of a reaction. A is the pre-exponential factor or frequency factor, which represent the rate of molecular collision and the probability of a successful collisions. EA is the activation energy, which is minimum energy required for a reaction to occur. R is the universal gas constant, that is 8.314 joule per mole per Kelvin. T is the absolute temperature. Let's take one more question. Explain the concept of ionic bond and provide an example of compound formed by an ionic bond. An ionic bond is a type of chemical bond that occurs between the two atoms significantly different electronegativities. It involves the transfer of one or more electron from one atom to another, resulting in the formation of oppositely charged ions. The atom that loses electrons become positively charged ion, it's called cation, while the atom that gains electron becomes negatively charged ion called anion. The attraction between the oppositely charged ions creates the ionic bond. Example, sodium chloride. Sodium Na is a metal that readily loses one electron, forming a sodium cation. It's represented as Na plus. Chlorine Cl is an non-metal and that readily accepts one electron, forming a chloride anion, that is Cl minus. In the formation of sodium chloride, the sodium atom donates an electron to the chlorine atom, resulting in the formation of Na plus and Cl minus ions. The strong electrostatic attraction between the Na plus and the Cl minus ions holds them together in a crystal lattice structure, forming the compound sodium chloride. You can observe that this is an electron. Sodium can give an electron and chlorine can take this electron. By losing electron, it attains a positive charge. By gaining electron, it attains negative charge. And the bond between the Na plus and Cl minus is called ionic bond. Let's go to the next slide. Describe the layer structure of ionic compounds, taking an example of cadmium iodide as an example. The layer structure of cadmium iodide can be described as follows. Alternating layers. The cadmium iodide crystal structure consists of alternating layers of cadmium ions Cd2 plus and iodide ions I minus stacked on top of each other. Cadmium layers. The cadmium layers are formed by a hexagonal arrangement of cadmium ions. Each cadmium ion is surrounded by 6 iodide ions, forming an octahedral coordination. The cadmium layers are held together by a weak van der Waals force of attraction. Iodide layers. The iodide layers are formed by a hexagonal arrangement of iodide ions. Each iodide ion is surrounded by 3 cadmium ions in the adjacent cadmium layer. Stocking. The cadmium and iodide layer stock on top of each other in an AB format sequence. In this arrangement, each iodide layer is sandwiched between the 2 cadmium layers. Let's take one more question. So what is hybridization? Mention the different types of hybridization. Hybridization is a concept in chemistry that describes the mixing of atomic orbital to form a newly hybrid orbitals. It is used to explain the molecular geometry and bonding properties of a molecules. In the process of hybridization, The atomic orbitals of the central atom in a molecule would recognize and combine to form a hybrid orbitals that have different shapes, energies, and orientation compared to the organic original atomic orbitals. The hybrid orbitals are more stable for describing the bonding and electron density distribution in molecules. The most common types of hybrid orbitals are sp orbital, sp2 hybrid orbitals, sp3 hybrid orbital, sp3d orbital, and sp3d2 hybrid orbitals, corresponding to the hybridization of s and p orbital. The specific type of hybridization depends on the number and the type of atomic orbitals involved in the hybridization process. Let's take one more question. What are intensive properties? Give two examples. The properties which depends upon the nature of the substance and are independent of the amount of substance present in the system are called intensive properties. Temperature, viscosity, surface tension, density, pressure, melting point, boiling point, freezing point, refractive index are the examples of intensive properties. What is residual entropy? Residual entropy is the difference between the non-equilibrium state and the crystal state of the substance close to a absolute zero. In the crystalline state at absolute zero, temperature of the substance like nitrogen dioxide, nitrous oxide, nitric oxide, carbon monoxide, hydrogen, and the ice appear to retain finite entropy, which is called as residual entropy. For example, in carbon monoxide and the nitrogen oxide, the two alternative arrangement of molecules are possible in the crystal lattice with the which are CO and OC, NO and ON. As the crystal, due to this type of arrangement, does not have definite structure, perfect order. Their entropy is not zero, but absolute zero. So, what I will do, I will stop at this stage and I will continue in the next class, next video.